This is test 2. We have sections 3-1, 3-2, 3-4, 4-1, 4-2. Now remember that 3-1 and 3-2 we did together as one section. And then we also did 4-1 and 4-2 like together as one section also. So really this is only 3 sections that we've covered in that sense, or 3 topics. 3-1 and 3-2 was all about acceleration. 3-4 was all about free fall motion, an object's dropped or thrown straight upward and it starts to fall after. And 4-1, 4-2 is about vectors. So your topics are acceleration, free fall motion, and vectors. Those are your 3 main topics. Now, within those topics, remember that you covered a lot of stuff with the quadratic formula, which is necessary for 3-4, and then with trigonometry, which is necessary for 4-1 and 4-2. So you have some inherent math skills that are also going to be tested on you. To start, I'll take that first question. That's fine. So it was page 120, number 16. It says you are driving up an inclined road. After 2.4 kilometers, you notice a roadside sign that indicates your elevation is increased by 160 meters. What is the angle of the road? So you have to draw yourself a diagram. That's what you have to do for this. So if you're driving up a road at a certain angle, this is 2.4 kilometers. And then after a certain time, you realize that your elevation is increased by 160 meters. Well, this was your starting point right here. So that means that your elevation has increased by 160 meters. Is that the height or is that the width of the triangle? If it says your elevation has increased by 160 meters, is it the height or the width of the triangle? Not the width. It's obviously the height by default. So elevation is... Remember, sorry, I'm saying width as the x. So I should have said the x or the y. It's the y component is what we're looking for. So the height of the triangle, again, is on the right side in this case. That would be 160 kilometers. No, meters. So what do you have to make sure to do for a problem like this then?
Oh.
Yeah, go ahead.
You have to make sure that they're both using the same stone. So 2,400 meters versus 160 meters.
Yeah, so you got to convert that hypotenuse right away. Because as soon as you try to do this, if you're going to look for this angle theta, that's what your goal is. That angle theta is going to be a very, 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 well, let's see, large angle in this. Well, no, it wouldn't even make sense, actually, because this number has to be greater than this number. You would get an answer that wouldn't make sense. You would actually get an error on your calculator. Did anybody try doing this and get an error? If you did do this and get an error, what it means is that this needs to be 2,400. Because you'd be doing, in this case, opposite over hypotenuse. This is sine. So it'd be sine inverse of 160 over 2.4. Well, that wouldn't make sense. You can't do that. It's impossible. You can never do a sine inverse or a cosine inverse of a number greater than 1. So the first thing to do, again, is to start, make this 2,400 meters. Then write out your trig ratio. Sine of theta equals opposite over hypotenuse. Okay, how do you find theta? You take the inverse of both sides. How would I figure out easily, without, well, you can use trig if you want actually too. How would I figure out the amount of range or displacement horizontally this person has covered? How would I figure out the horizontal displacement this person has covered in this example? What would I do, Jack?
You would just put the equation in your calculator. Negative sine of 160 over 2,400.
That'll give me the angle, yeah. That'll give me the angle. And I have to know, how would I figure out this width of the triangle? Pythagorean theorem, okay? Go right to Pythagorean theorem. What I'm trying to say is there's no need to use trig to find out lengths and have 2 of the other lengths there. Okay, but again, this is how you'd find the angle of inclination, you'd call that, really. And another word, when it goes down, instead of inclination, yeah, declination, really. But yeah, it would be like declination, but declination, okay? Or depression. Some people say the angle of depression, the angle at which you're looking down. That's it for that kind of a problem. This is a relatively straightforward, simple kind of problem. This would be like multiple choice, actually. This wouldn't even be on a math part. This is too easy for a math part. Okay, something this simple. A math part would be something where a person moves north, then moves like southeast at an angle, then moves northeast, find the overall displacement. We have to do like 3 different parts to it. That would be more of a mathematical kind of a problem. What questions do you have before I specifically point out things that I want to go over? What questions besides this do you have? Yeah, absolutely. Well, let's do one of those first. So let's say that a person moves first. They start at some starting point. Okay, and I'm gonna tell you what it is, but you have to be able to visualize this as I'm drawing it. Okay, so if later you're like, how did he get the diagram? You should listen to the video without actually looking at what's happening. You follow what I'm saying? So later on, if you want to rewatch this video, hit play, but change the window and just listen to what it says and try and redraw the diagram, practicing it. So a person moves 2 miles, walks 2 miles north. That's supposed to be a straight line. Sorry, walks 2 miles north, stops, and then walks 1 mile at an angle of 20 degrees northeast, and then walks 1 mile at an angle of 20 degrees northeast. Okay, those are my lengths, 1 and 2. The person then decides to stop, have lunch, relax, then go, another 1.5 miles at an angle of 60 degrees southeast. Another 1.5 miles, 60 degrees southeast. So right away, I think this is east. I need to go south of east, so go below that line at 60 degrees. And this is another 1.5 miles. And the final question says, determine the overall displacement from start to finish. Hey, it's hard to see, but I'll put a capital R there so you can see it. And we're looking for capital R. Yeah, come on. There you go. All right, so that's what our goal is. So to find capital R, we have to think about the fact that capital R is really the hypotenuse to its own triangle. So if you need to do this to visualize, go ahead and do it. But look, a dashed line here, and a dashed line here. And that's your dashed line. Across and up. So go ahead and draw one in if it helps you. And that's what your goal is. You need to find the lengths of these dashed lines. This X and this Y. That's what we're trying to figure out. If you could find those two lengths, you could then use Pythagorean theorem. Now, I'm going to go through this on my own. I'm not going to take suggestions from you just for the sake of time so we could all see through this problem. You guys saw how to do this in the video, but let me show you maybe a tabular approach that would help. If some people have trouble with organization with this kind of a topic, so I took this approach with last year's class, and it's just using a table. Somebody asked me to do it, and I remember actually doing it on the actual when we reviewed for the test. They were like, "Is there another way to look at this?" So I came up with another way, and I was thinking about it also. So I wrote this down for myself. So the way I taught them to do it, if they had trouble with organization, if you get what you're doing, please keep doing what you're doing already. But if you're like, I'm really lost with this topic right now, maybe try this approach instead. So I had them start an approach where they had the vector length here, they had the angle here, then they had the x value and the y value. This was the approach I had them take. So list your vectors first. The vector of 2. The vector of 2. Does that have any angle? Does that have any angle involved in it? Look at the length of vector 2. What did we say in vector 2? Where was the person moving? What was the word I used? North. Thank you, Travis. North. So north is straight up and down, right? So is that in the x or the y direction? In the y direction only. If you can't see that by now, you got to stop and look at this and honestly look. It's going up. That's the y direction. So it's 2 in the y direction. I don't need an angle. I don't need an x component. It's 2 in the y direction only. So put a 2 in the y direction. Again, the first example is not a great one to give. And the next one with the angle, you'll see what we're going to do. Then the next one, the vector length is 1. That's at the top of the diagram up here. Now, this person has an angle of 20 degrees. 20 degrees northeast. North of east. So that 20 degrees goes right here. Now, after that, the question is, what is the x and what is the y? Well, what does northeast mean? It means positive x, positive y. You're in the first quadrant. Again, visualize this as your origin right here. This is your origin. Imagine now that this is the y-axis and this is the x-axis. This is east and then you go north. It's, again, north of east. So positive, positive. So these are both positives already. We know that much at least. That's good. And then all you have to do is write down the thing that I had you memorize. The vector times the cosine of theta. The vector times the sine of theta. Just write those down. That's all you have to do. The vector is length of 1 times the cosine of theta. And this vector length 1 times the sine of theta. So that's vector, I call it vector 2. The second vector, which is length 1, the second vector's component is broken down. So again, this is the x part of it, And I'll point to it so you can see what I'm saying. This part right here, this number is literally this length right here. From here to right there. And then this height right here, this y, is this right here. Again, that's the height. So I'm breaking this vector right here into its components. There's the triangle right there. Then I take a look at this one. This is the one that's going to throw most students for a loop. Why might this one be a little bit trickier? Or what might be the mistake that some people may make with this vector as opposed to this vector? Look at the angle itself. Look at the angle itself. Here's your new origin. Here's your new origin. This is your x-axis. This is your y-axis. What quadrant are we in for this vector? You don't have to give me the number, but give me at least the signs at least, yeah.
The fourth quadrant?
Yeah, the fourth quadrant. So x is positive, but then I go down, don't I? So I'm going positive in the x, which is good, that's fine. So positive in the x. But it looks like I'm going negative in the y direction. So after this person goes all the way over here, they're coming all the way down here and ending up here, but by doing it by cutting across the field. So they're going positive x, but then negative y. So the y direction should have a negative sign. Okay, that's going to be a negative sign. These are not negative signs. See, this is just empty spots. There's no component. The length of the vector is 1.5. The angle is 60 degrees. All you got to do is plug those in. 1.5 cosine 60. 1.5 sine 60. Now, what have we done? Or why have we done this? What we've done is this. We've taken each vector and broken it into its component pieces. Now what we have to do is add up these components. Add up, write down your x value. See the x column right here? Add those up. You'll get this length right here. From here all the way to here. Add up your y value straight down. You'll get this height right here. So this might be a more organized way for some of you to figure out what the overall components are for the resulting triangle so that you can get the final result in R. Okay, so add straight down. I'm not going to do this for you right now. You guys can check on a calculator. Add these numbers right here. Put them across right here. Add these three numbers right here. That sum is going to be the height of the triangle right here. Once you have the base and the height, you could find the hypotenuse using Pythagorean theorem. Okay, this is just an organized approach to the exact same thing that we've been doing, but we've been drawing a lot of it so you can visually see it. You don't see it as much with the table as what's going on with the diagram, but if you remember how to do this, where you take the vector, put the angle there, break up the x and y component, but look, again, this is what I've been telling you, cosine theta, sine theta, that's where that's coming up. What's in front? The vector length. What's in front? The vector length. That comes from right here. So it's the same thing you've been doing, just in a table, so it makes it easier to organize.
So for the x, it'll always be cosine?
Yep. And for the y, it'll always be sine. Okay, now remember, Gus, why did I put a sine at the top one? Because the first directional was only north. The first motion of this person was 2 miles north. There was no east, there was no west, there was only north, there was no angle involved. The minute there's no angle, and it's only north, I don't have to worry about the x, it's all in the y direction. Okay, remember, components mean pieces of it. So if something is only going west, or like they say west this way, it would be just negative x. It wouldn't have any y component at all. Again, vertical motion is y, horizontal is x. So it depends on the approach you take for this. Anybody got those numbers for me? Anyone sum those together? I can move on to another problem. It's not a big deal. But if you want to check later, then at least check on your own, okay? Sum those values together. You'll get an answer here for x. You get an answer here for y. That's the sum of the x's. That's the sum of the y's right there. The sum of the x's goes here. The sum of the y's goes up there in the diagram. And then figure out the length of r. You also, if you need to be able to, which you will, need to be able to figure out the angle theta, there's the angle theta right there. Okay, remember, from starting to ending point, you're looking at the change. You started there at the bottom left. If you start right here and you end right here, you're determining this angle theta right there. If y turned out to be negative, it means your diagram was just not drawn to scale. Maybe this line should have extended further down here, and then it would be over and down. So you get angle theta, God bless you, right there. But it would still be the same thing. To find theta, you could use the tangent inverse of the y value over the x value. And again, what y value and x value? We're talking about these values right here. Once you get these values here, remember, how do you find this angle? This is opposite over adjacent. So use tangent. The tangent of theta equals y over x. So theta equals the tangent inverse of y over x. Here's what I would do. If you're like, I'm really confused right now, and I'm not really sure what to do. Tonight, change the numbers, change the problem, make a new problem yourself. You start with the problem where a person walks east for a while, then they walk south, then they walk northeast maybe. That would be the tough one. But take the same exact approach and try it. Sum these values together, straight down the columns, and you'll have your overall result. If you're also confused when practicing and you're doing it algebraically, use graph paper. And if you get like something where it says, an object moves 3.7 miles and 2.6 miles, try to estimate on the grid lines what it should look like. Okay, if you have a protractor, that'd be even better. But the angles you should be able to estimate. Right, this is 0, this is 90, this is 45, 30, 60. You should know general angles from geometry. So a lot of your math is coming up in this course. Again, 0, 30, 45, 60, 90, that's how you go through your 0 to 90. So depending upon the angle that's given in the problem, try to make your graph or your sketch reasonable, so it looks reasonable again. If your graph or your sketch is way off, you get an answer that doesn't correspond, it's because your sketch was most likely off, or the work you did was wrong. So you have to figure out which one of those two things it could be either of those factors. What other questions on this one? You should be able to also do this kind of a problem graphically. So if a problem says, let's say, you would definitely have a graph for this, by the way. So if you're doing it graphically, you'd have a grid line in front of you. But let's say the problem says, what is the sum of vector A and vector B? That's what the question asks. What is the sum of those vectors? And vector A is given by this length here. And vector B is given by the following length here. And that's the question. Find the sum of A and B. Okay, find the sum of A and B. You did this in class. You did it the day I was not here. All you have to do is connect them. That's it. Just don't pick up your pencil. Redraw vector A and just draw vector B from the end of it. So here, I'm going to draw on the right the sum. Here's vector A, and here's vector B. So how do I find out the overall length? It's that length right there. Okay, again, you're going to be doing this graphically. You'll have a grid line. You don't have to be able to calculate angles and stuff. You don't have to worry about that. Okay, it'll be on an actual graph with grid lines. So you'll be able to figure out what that actually is. And again, since there'll be grid lines, you could count how many boxes over and how many boxes down to get the overall answer you're looking for, R. Okay, again, think about it logically. Follow the pencil the whole way and continue down. And this is from beginning to end. To figure out the length from beginning to end, I need to know what this is and what this is right here. And it will be on a graph. So since this is on a graph, you could literally just count the boxes over, count the boxes down, you'll have your width, you'll have your height of the triangle, use Pythagorean theorem, you could find out what the length itself is. Here, if you need to practice for this, I'm trying to give you guys examples of how to practice for this kind of a test. If you need to practice, honestly, pick arbitrary lengths. It doesn't matter. Make a vector up. Grab a piece of graph paper, make vector A 7 boxes over, 2 boxes up. Make vector B 4 boxes over, 3 boxes down. Add A and B together by just practicing drawing them and drawing the exact same proportion that they're drawn on the actual graph paper. Okay, just practice doing it over and over and it'll make it a little bit easier for you. I think 1 or 2 of your homeworks or problem sets, had you calculating things graphically also. So in that case, when it says that, I'm not going to ask you to do it with a protractor. It just takes a little bit more time. There's a lot of room for error. And to be honest, I would push that, but most of the design for engineering and science is going to be done on CAD anyway these days. Most people don't even use protractors for that application at least. Okay, for other applications, sure, but not for that. What other stuff? What other questions? So that's really only 4.1 and 4.2 you've asked about so far. There's still a lot of stuff from 3.1, 3.2, and 3.4, yeah. In 3.1? Do you know what page by any chance? Or in the actual section or at the end of the chapter with the review? In the problem sets. But sometimes the problem sets are in the section, sometimes they're in the end of the chapter. What number? Number 8. I don't think it could have been 8. In 3.1 there is no number 8. What other stuff, guys? Can you find the actual problem? I'm in section 3.1. There's no number 8 here. Starts at number 11. 18 maybe? I don't know. Is it interpreting a graph, or what does it look like?
It's the interpretive graph.
It is the graph one. Okay, yeah. So this is a good question. So you have a velocity time graph. This is something that you absolutely 100% have to be able to do on the test. In the last test, what kind of graphs did you guys have? Yeah, thank you for listening and responding. Distance time or position time graph in the previous test. This is now velocity time. If you have the velocity time graph, and technically I should put it in all 4 quadrants, so I should move this up, but can I do that? No, I don't really care right now. So let's say we've got an object that moves in the following fashion. Okay? There's the motion of the object. Again, this is the what of the object? You should use the word motion. The what? Yeah, that's velocity. The velocity. This is not the position. So please don't tell me this person walks and then stops. At that plateau at the top, they are not stopped. So many of you on the labs confuse this. Again, this person is moving with some velocity, well, initially no velocity. Then the person gets more velocity, more velocity, more velocity. If they're gaining velocity, what are they doing? Accelerating. Very good. Right away, you should be able to answer that. When you hear they are gaining or losing velocity, acceleration, whether it's positive or negative. Then they get to a point where they reach their max velocity right here. And then what do? Thank you. Very good, Mary. And then they keep going, but at a constant velocity in this region. This is not stopping motion. This is not stopping like it was in the previous graph, because this is a graph of velocity. So increasing velocity or acceleration, then constant velocity. So what's the acceleration at the top? When it's constant velocity, what's the acceleration? There is no acceleration. Okay, you got positive acceleration and then no acceleration. How come? Because the slope of the line is the acceleration. The slope of the line is what was the slope of the position graph? A position graph. If you found the slope of that, what did you get? Think back to last test. If you found the slope of a position graph, you got something. Gus?
Was it velocity?
It was velocity. And Gus, good deductive reasoning there. If you didn't know, we were talking about change of position being velocity. This is change of velocity. It is acceleration. Okay, just think about the change and what it physically is. Then it has a negative acceleration for a while, right? Suddenly what happens? The velocity decreases. What's the velocity right here? 0. So what happens right here? It stops. The object stops. So if this, I could ask this question so many ways. Do you see what I'm saying? I could put one graph and ask you 5 multiple choice questions. Explain, or at what time does the object stop? Well, you could pick either of these 2 answers, depending on what the choice is. At what point does the object have constant motion? Either of these ranges, depending on what the multiple choice is. At what point in the graph is the object losing velocity? Anywhere along this region right here, where you see negative acceleration. So there are so many questions that can come from one simple graph. Okay, from one graph. So what you need to do is do what we're doing here. Draw yourself some graphs. Analyze it. Write what's going on. Write that this is acceleration, that's negative. And then here again, the acceleration is 0. And then again, the acceleration is positive. Well, then I could keep writing further. I could say the object stops here, here, and here. There's no motion. Those 3 points, those are your roots, or the zeros of the function. Okay, those are the x-intercepts. Those values, there's no velocity there. So you need to be able to interpret a velocity time graph for sure. Good question, Tiana. Okay, a problem that is 100% going to be on the test. Okay, maybe more than once, meaning you might have to interpret more than one graph. Remember that table we made and we talked for a while about velocity increasing and speeding up and slowing down and stuff with acceleration? You have to be able to understand those terminologies. So again, let's discuss real quick. If I'm moving to the right, I'm moving this way. What's the only way I can speed up? So my velocity is positive, for sure. My velocity is positive. How do I speed up? If I have what? I have to have positive what? What's the other word? Acceleration, to speed up. What if I'm going this way with negative velocity? Then I need negative acceleration. That will also speed up. Think about it. I'm going this way already, and the wind is pushing me more that way. It's accelerating me negatively. I would be speeding up. But I'd be speeding up in the negative direction in the second scenario. Whereas in the first scenario, I'd be speeding up in the positive direction. When am I ever slowing down? There's one simple rule to remember. We came up with this conclusion in class. You're slowing down when what? It's a simple way to remember. Not at rest. When you're at rest, you're at rest. You're actually at rest. Yes. When velocity and acceleration have opposite signs. Think about it. I'm moving to the right at positive velocity. Suddenly there's negative acceleration. That's what wind is doing, slowing me down, pushing back. If I'm moving negatively and acceleration is positive, I'm still also slowing down because acceleration is pushing me that way until I eventually stop. Okay, so the only time you can slow down is when your signs are opposite. When the signs are the same, you're speeding up. That's the easy way to remember. Okay, that's the conclusion at the end of that table we came up with there.
So the signs for velocity and
Acceleration?
acceleration need to be opposite.
For slowing down. For slowing down, yes. You need to have memorized that the x component is cosine, the y component is sine. It's going to come up on the test several times. Okay, several times. Hold off on that. I'm just going to go further with it. We talked about vectors, and in the beginning of the video, you listened, or if you remember when Anthony was here doing that with you guys. In the beginning of it, he talked about what a vector really is. What is a vector, actually? Anybody remember? You don't have to spit out the exact definition, but give me a general definition of what a vector is. For example, displacement is a vector, distance is not. Remember that? Displacement is a vector, distance is not. Remember?
It's a distance with direction.
Yes, it's some length with direction. The key is direction. The key is direction. So a vector must have direction. 72 degrees Fahrenheit, is that a vector? No. 72 degrees Fahrenheit, it's not a vector whatsoever. 32 pounds. No. 27 meters northeast. Yes. Right? You see what I'm saying? The minute you give a direction, you have a vector length itself. You need to have a magnitude and a direction. You know that you have commutative nature of vectors. So if I ask you to prove that adding A and B together and B and A together are the same thing, you just need to do it twice. Do it once going A and then B, the second time going B and then A. I'm at the exact same point. Now let me show you what I'm saying for this. So you can do this graphically or you can show it with a quick sketch. Let's say this is vector A and this is vector B. That's A plus B right there. That's literally what it is. A plus B gives me this solution here. That's the result. Well, what if I do B plus A? It's the exact same thing. Go down first like this, there's B, and go over, there's A. It's the exact same thing. Again, that's A and that's B. So again, what's our rule? A plus B equals B plus A. And these are in vectors. There's a little arrows above each of those letters. Sorry. Okay? This is the commutative law of addition we learn in 6th grade, maybe? Even earlier than that. But it's vector law as well. Does not matter which one you do first. To prove it, you could show it like that. You might have to think about that algebraically as you go through. Always draw diagrams whenever possible. Always draw diagrams, please, please. Yeah, Marilyn.
When you're doing this, you're not literally doing, like, let's say A equals 50 and...
I'm not actually plugging in numbers. No. I'm showing just with a diagram, that's all. No numbers are needed for that. You don't need numbers at all. You don't need a 50, you don't need a 20 to prove that you're talking about the commutative part, right?
Yeah.
All you got to do is show that when A and B are summed that way, or B and A are summed that way, you end up at the exact same point. You started here, you ended here. This is the result, that white line. Whether you do AB or BA, it's the exact same answer. Ask it differently then. Go ahead. It's not answer. Go ahead.
Yeah. For this, am I adding segments, like A and B, or am I adding like the triangle?
No triangles needed for this. Yeah, no triangles. This is just an example graphically or showing sketching wise that it's commutative. If there's a problem that the person moves this way and then at this angle and this, and you want to find the overall resultant, then you're adding those little triangle lengths like we did with the table and stuff for sure. This is just sketching by hand. This is not.
What are you adding that equals the same thing?
So if I go in this direction and in this direction, I end up here, right?
Mm-hmm.
But instead of going up and then down, what if I go down and then up? Don't I end up at the same point?
Yeah.
So as a result, it doesn't matter which vector length I go first. And it's like in the city. Think about it. You've done this before. You need to get 86 in Lex. How many options do you have? Go over to Lex, go up. Go up to 84, over to Lex, go up. Go up to 85, over to Lex, go up. Go up to 86, over to Lex. Right? There are so many ways to get there. They're all the same thing. That's what this is showing here. Okay? It's the same thing every time. Now, we have not talked about sections 3.1 and 3.2. Let's talk about those for a little while. Mathematical, we have not. Okay, 3.1 and 3.2, you had three formulas. Well, there's the general formula first. That's the definition of acceleration. This was like the overarching formula for this entire section. Then we actually had our formulas. We had VF equals VI plus AT. We had VF squared equals VI squared plus 2AX. And then finally, x equals VIT plus 1/2 AT squared. Now, these three equations can all be written with y instead of x. In this chapter, we are only looking at one-dimensional motion. It's either up and down or left and right. It's not at an angle. It's not something that's launched like a football. So you don't have to worry about that yet. That's in the next section, actually. So for now, use either of these equations or any of these equations, but put a y in where the x is when you need it. How do you know which equation to choose? Seriously, how do you know which equation to choose? What's the approach I keep telling you to take on all these problems?
Because don't some equations have parts of each equation?
Exactly. See what you have. What parts are missing? So if I give you a problem, okay, sometimes the hardest parts of problems I notice for students is actually listing the givens. It's actually just listing the givens. The way you can practice that, honestly, is by actually going through more problems. But let me give you an example. Okay, an object is dropped, and it takes 4.2 seconds to hit the ground. Determine the final velocity and the displacement. Okay, so right away, an object is dropped. What do you write when an object is dropped?
The initial is 0.
Yeah, VI is 0. All right, I got that. That's good. It takes 4 seconds to hit the ground, I say. What is that? The time. Okay, right away, that's what you've got. Automatically, it's dropped. When it's dropped, what's the acceleration? When it's dropped, what's the acceleration? Yeah, negative 9.81. So that's what I've got automatically. It's dropped. It's dropped. That means it's vertical motion. If I said it's rolled left to right, then you need acceleration. It has to be given, or something would have to be given for you. But when it's dropped, when it's in free fall motion, that's your acceleration. And then I asked you, what is the velocity with which it hits the ground? And how far does it travel? What is the vertical displacement? So how do you find the velocity with which it hits the ground? What are we looking for there? The velocity with which it hits the ground. What am I looking for? Yeah, and use context clues. You've got initial. You're probably looking for final. It's the only other velocity available here, right? So you're probably finding final velocity. And then I said, find out the overall displacement. Are we looking at x or y in this case for displacement? Y. Why are we looking for y? Yeah, it's up and down. Again, I'm dropping the object. When I drop something, it falls straight down to the ground. Okay, so that's why it's called free fall motion. So this kind of a question is really out of section 3.4 because it's free fall motion, but it's using all the equations from 3.1 and 3.2 also. You could have a horizontal motion with acceleration from 3.1 and 3.2, and we'll do an example of that. But this is an example where we have vertical motion. So if the case is that VI is 0 here, first of all, I don't need the first formula, I can tell you right away. I'm not going to need to calculate acceleration. I only use that first one when I need to find acceleration. Is that clear? Everybody see that? Please do not use the first formula unless you're finding acceleration. Some of you have been trying to use that to find like the velocity, but you have to put VF minus VI, and then you have to rearrange it. Use the one that's already rearranged. Okay, so use the stuff that you're seeing below here. So yeah, more.
Can you still get like the answer?
The first one?
Yeah.
You could, but you have to replace delta V with VF minus VI, then you have to resolve for VF. Why would you bother doing that? This is already solved for VF. Doesn't make sense to go through all that effort. Okay? So right away, I'm trying to find out the VF and the Y value. VF and Y value. VF and Y value. What am I going to use? Which formula? Which formulas? Which ones? Come on. I don't see Y in any of these formulas, so what should I visualize? Where should the y go in all these formulas? It's not there. Where the x is. So start by doing this, please, if it helps. Put a y in these places, right here and here. Those are both y's now. Okay? Again, on your formula sheet, what do you see? You see x. It just means displacement. I'm not going to rewrite the same formulas with just a different letter. When it's vertical motion, you just put the letter y. That's the only difference. Now, if I want to find the VF value, what am I using? Which formula? Right away, I cannot use the third, so please do not answer with the third to find VF. It's one of those two, obviously. Which of those two is it going to be? The first one. What do I not have in the second one that I would need to find out VF? I would need also y. So do I have y? I don't have y. So to find out VF using this one, I need to know all of these. I don't know all of these, so I'm done. But I do know time, I do know acceleration, and I do indeed know VI. Is that clear? Plug those in, you get VF. How do you get the y value? The y value. And there are multiple answers to this, so there's two correct answers. True?
Once you find VF, you put it back into the second equation.
Yeah, you can, once you get your VF, you can plug that in. You know VI, you know y, solve for y. Second approach, you want to take the second approach too? What's the formula I haven't used yet? Yeah, look at this. VI is what? 0. That drops off. Acceleration, negative 9.81. Time, 4 seconds. Square the 4 seconds, that becomes 16. 16 times negative 9.81 times 1/2 will give you y. Why will y be negative in this problem? Why will your answer for y be negative?
Because you're going down.
Thank you, guys. Very good. You're dropping an object, so it is moving down to the ground. Your displacement would be down, which is negative. This exact same problem can be taken from a horizontal approach or horizontal perspective. Let's say, for example, I'll give you another scenario now. Okay, scenario 2. Let's say that an object, you can jot this down or just write down the givens as you think about them. An object moves with a velocity of 5 meters per second. An object moves at a velocity of 5 meters per second. It then accelerates at a rate of 2 meters per second squared. So it's moving with a velocity of 5 meters per second. It then accelerates with an acceleration of 2 meters per second squared. Determine the time it would take to get up to a velocity. Well, let's say no. Determine the time it would take to cover 4 meters. To cover 4 meters. That's too little. 40 meters. 40 meters. That's why when I do your tests, I always make sure the numbers work. So an object moves with a velocity of 5 meters per second. It begins to accelerate with an acceleration of 2 meters per second squared. Determine how long it will take to cover a displacement of 40 meters. So right off the bat, what do I have? Give me some givens. Give me one of them. Bernadette.
VI equals 5.
Yeah, VI equals 5. That's the starting velocity. Next, Martha.
Acceleration is 2 meters.
2 meters per second squared. Okay. And then finally, x is 40 meters. Those are my givens. Very good. Somebody else now. What am I looking for? What am I trying to find? What am I trying to find in this problem? Should all have had this written down. This was the obvious. Bruce? Time. We're looking for time. Okay? So, we look at this problem. We say to ourselves, well, there's nothing to do with VF, right? Anybody say anything with VF in this problem? Unfortunately not. So we probably can't use either of those formulas. So you jump right to the third formula. X equals VIT plus 1/2 AT squared. Now, if you are struggling with the quadratic formulas, you need to practice. Because look, here it's coming up right now. It's about to happen. 40, 5, 9, 2 goes in here. You got T squared, you got a T. Quadratic formula is necessary here. It is necessary. Now, if you want to be lazy and not use it, you could, but you then have to use 2 equations to solve this problem. You'd have to use VF squared equals VI squared plus 2AX to find VF, and then use VF equals VI plus AT to find time. So you'd have to find VF first and then find time. You can do that and go through the problem twice, or just learn how to use the quadratic formula and graph on the calculator, or just do it by hand. So plug in at this point. 40, and this is one of the times I always say plug in, because you can't solve for t. There's no way to solve for t. It's in 2 spots. 5t plus 1/2 times acceleration times t squared. So you can tell that it's a quadratic because t is here and t squared is here. That's how you know it's a quadratic. get everything on one side of the equation. So I've got half of 2, which is just 1, right? Please don't leave this alone. Half of 2 is simply 1. So it turns out that t squared is by itself, plus 5t. How do I get the 40 over? How do I get the 40 over? Quick, everybody, get the 40 over. Thank you. Subtract. Should be second instinct, right? Right away. T squared plus 5t minus 40. Solve. Okay? And you might want to say, oh, let me factor this. Maybe I can factor this, right? And maybe you can. There's a good chance you can't. I'm going to tell you now. Hints. There's a good chance you can't. Don't try and factor on the test. Okay, it won't be factored. I'm going to tell you that right now. Especially if it's anything with vertical motion, because your vertical motion, your acceleration, is 9.81, which will make this coefficient negative 4.905. Okay, so that's not going to be a 1 in the front there. You're not going to have that value. So you have to use your quadratic formula. Okay, please go ahead and watch the video on that if you're confused on that still, or maybe today at some point come see me.
Wait, so then for that,
How many answers are you going to get?
t squared 2, and then t squared would be,
The A value would be 1.
so that would be a.
A is 1, B is 5, C is negative 40. Literally just plug it in right there. Or, honestly, Gus, if you like the calculator more, I also put those videos from class that you watched. One of them is on how to solve this using a calculator only. I don't care which way you do it, honestly. You can use the calculator test, you might as well save time. So if you want to use the calculator to solve this, and all you have to do in the calculator is find the x-intercepts. Plug this into your y1 using x instead of t, and just find the x-intercepts. Those are your those are your answers. Remember, the x-intercepts are the solutions, really. So you can do this either way. Depending upon which approach you feel more comfortable with, it's up to you. Okay, it's up to you to choose. I'm going to see what else I haven't talked about. We have about is it a B-day? Okay, we have about a minute. We talked about this quickly, but you're throwing an object up, and I ask you, when is it going to reach a height of 20 meters, or reach the window ledge? Okay, of 20 meters. And say you get 2 answers for time. You get 2 answers. Why would you get 2 answers? Why would you get 2 answers? You throw an object upward, you want to know when it's going to reach the window. Now, I'm not saying it's going to stop when it reaches the window, it goes beyond the window. So why would you get 2 answers? It's going to go past that mark, and then what's going to happen? It's going to go back down again. Okay, significance of those answers. One's on the way up, one's on